Now introducing, from Amador Valley High School, their unmanned aerial vehicle team, AmadorUAVs.
Hi, I'm Rachel. I've been a part of AmadorUAVs for 2 years. I'm the current mechanical lead, and I'm also this year's competition team lead.
Hello, I'm Nikhil Sonkad, and I've been here at AmadorUAVs for 4 years. This year, I'm software lead.
Hi, I'm Abe. I've been a part of AmadorUAVs for 2 years, and I'm the electrical VP.
Hi, I'm Christopher. I've been with UAVs for 2 years, and this year I'm a mechanical member and manage the payload project.
I'm Amber. I've been in UAVs for a year and I'm working on payload.
Hi, I'm Jerry and I've been in UAVs for like 2 years. And what I'm working on right now is payload, but I've done EFCs, the leg clamps, and other things.
Okay. My name is Ardem. I've been in this club for 1 year. I'm in the electrical division and I'm working on batteries and power systems.
Hi, my name is Edward Chen. I've been part of UAVs for 1 year and I'm part of electrical. And I have been working on gimbal.
Hi, I'm Verdon. This is my second year in the software division, and I've been working on vision and simulation.
Hi, my name is Prada Mehta, and I've been in software for 2 years, and I've been working on the autopilot.
When deciding on our system and components, we decided to mostly use the requirement needed to reach 5 miles in range without refueling. To do this, we first decided that we'd ideally need enough thrust to lift 2.5 times the actual weight of the drone, giving us enough wiggle room in case something went wrong. We also decided to use a coaxial octorotor, giving us efficiency in design, as we did not need as much material to mount the motors to the arms as if we would have done 8 arms instead. For our batteries, we looked at the power needed to run the motors and ESCs for about 20 minutes continuously, and the weight of the batteries also came into consideration, as the more weight you add to the drone, the less efficient it will be. For our flight controller and system, we looked for both redundancy and stability, and we found that the Pixhawk 6S was the best system for our needs. For a gimbal stabilizer for our drone, we decided to make our own, as the options on the market were either too big or too expensive for our needs. For the payload system, we looked to make it as small and efficient as possible, while also keeping in mind the speed needed, as we did not want to keep the drone in the air for longer than needed.
Our unmanned aerial system consists of a ground station that communicates with the UAV via a set of Holybro P900 telemetry radios in order to accomplish a mission, which aims to deliver payloads to various ODLCs along a given course. Payloads are delivered using a winch system which implements a disc brake in order to safely drop water bottles from Boreas. In order to detect the waypoints at which payloads are dropped at, we use an imaging source camera. In terms of team operations, most of the mission is operated autonomously, while the safety of the ground crew near the aerial vehicle is ensured by a designated safety pilot, which is able to take full control of the UAV in worst-case scenarios. In addition to the safety pilot, we have a ground control station operator alongside another operator whose job would be to switch batteries and payloads.
For our imaging sensor, we chose to use an industrial-grade camera provided from the imaging source company. The camera incorporates a 1-inch sensor capable of recording at 18 frames a second with a resolution of 20 megapixels. Attached to the camera, we have a 35mm lens, which allows for 160 pixels of horizontal resolutions for each ODLC from a height of 300 feet. In order to classify each ODLC on the ground, we use a series of YOLO V8 models. First, we use a YOLO V8 model trained on thousands of simulated images to pick out and localize each ODLC from a height of 300 feet. We use this YOLO V8 model to crop out a bounding box with each ODLC in it. After that, we use an open source U²net model to crop out the shape and the silhouette of each ODLC from the square bounding box. For instance, we can isolate a triangle, a square, or a circle. After this, we pass our cropped image through character and shape detection using 2 more YOLO V8 models. Finally, for color detection, we blur the cropped image, quantize the colors, and run one final YOLO V8 model.
To test our imaging system, we flew Boreas up to 125 feet and used the Jetson to capture images. We then took those same images and used them to test our imaging algorithm on the ground before running it on Boreas. The algorithm had a 92% success rate when finding the ODLCs, and the resolution from the images was about 400 by 400 pixels when taken from 125 feet above ground level.
Our payload drop design uses a spool slowed down by a disc brake. So basically what we do is we drop the payload, we let it free fall on the spool, and then we use the disc brakes to slow the spool down to make the payload come to a stop and enter at a safe velocity. So the way our disc brake works, it's kind of like what you can envision on a car. It has calipers that push the brake pads in towards the brake rotor, in this case being the side of the spool. But unlike a car's, instead of using hydraulic fluid, we opted for a screw design. So as the screws spin, they go towards like the brake pads and push them in onto the spool. So the reason we did this instead of a hydraulics was the hydraulics would be annoying to get all the air out of the system and deal with the hydraulic fluid. And our calipers are actuated by gears that are both spun by one singular servo. That way we can minimize the complexity of our system.
To test our airdrop system, we completed over 40 airdrops, some of which were performed on our test drone, Macron, to see if the payload mechanism was working as expected and we could move on to testing on Boreas. Our airdrop success rate was 90% on Boreas, missing 2 out of 20 attempts due to severe wind that affected our line connecting the water bottle to the payload mechanism. Otherwise, all of our airdrops performed as expected, landing within 20 feet from the target. The 90th percentile distance that our payload landed was approximately 10 feet from the center, with the distance often being caused by the wind blowing the descent line around.
For communication between the ground station and the UAS, we use 2 Holybro P900 telemetry radios. Each radio is rated for a range of up to 40 miles. The frequencies range from between 902 and 928 megahertz. Over the radios, a series of Mavlink messages are sent. For instance, the ground station sends arming messages to the radio on the drone, and the drone sends back information containing battery capacity, altitude, attitude, position, velocity, and others.
To test the range of our communication subsystem, we flew out over 1,000 feet away from the ground control station and monitored the connection. The P900 telemetry radios were successful in transmitting 75% of the data from Boreas back to the ground control station, even when 1,000 feet away. The main section of Boreas's airframe is comprised of the electronics cage, which is formed by 2 carbon fiber plates that sandwich the arm tubes. This setup allows for maximum protection of our flight controller, the Pixhawk 6X, an onboard computer, a Jetson Orin, protecting both from outside elements. Mounted along the outside of the cage are our Mixa ESCs, which are protected by custom-designed 3D printed cases. These ESCs allow for superior efficiency and performance while flying, greatly benefiting the system's overall performance. In addition to the performance benefits, the Mixa ESCs are wired on redundant CAN buses, with the top 4 motors on one line and the bottom 4 on a second line. This allows for extra redundancy, as if one CAN bus becomes inoperable for any reason, there's a second line to keep the drone stable enough to land. To go with the Mixa ESCs, we chose to use T-Motor MN601S motors, as they are incredibly efficient and powerful. Each one of these motors is rated for 14.9 pounds of thrust, and Boreas is capable of producing 115 pounds of thrust when at full throttle. To power Boreas, we chose to use 2 WeLion 6S 30 amp-hour batteries, which provides enough power for Boreas to fly continuously for over 30 minutes in optimal conditions. Underneath the electronics cage, there is an auxiliary plate which is used to mount components such as the airdrop mechanism and our custom gimbal. To ensure that Boreas is suitable for mission tasks, we put it through rigorous flight testing. After over 30 hours of flight time on Boreas, we are confident that our system will be able to complete the competition tasks. The battery lifespan for one full charge is about 30 minutes of constant flying, and at an average speed of 32 miles per hour, Boreas should not have any trouble completing a mission in less than 30 minutes.
However, this year, we decided to optimize our path further. We realized that in the rules, there was a 25-foot distance from the waypoints that we had to be in order to hit the waypoint. So in order to do that, we used a custom Pure Pursuit controller, which used 25 feet as the K value for the radius of the circle, in which we were able to smooth the corners for the waypoints, allowing the drone to travel in a more effective and efficient path. However, because of this, in Q ground control, as more waypoints are added, the flight time of the drone takes longer as the drone waits at each waypoint. So we decided to optimize the number of waypoints in the path by implementing a line consolidator, where we were able to determine the slope between the waypoints and consolidate the waypoints if the slope between them was similar. And so in doing this, we were able to get around a 10% reduction in the flight path.
To test our autopilot, we set up a variety of different tests, most of which consisted of flight paths of varying lengths and observing the waypoint accuracy. During these tests, we flew a total of 684 waypoints with an average waypoint error of 5 feet. While testing Boreas's autopilot, we completed over 45 autonomous flights ranging in length from 200 feet to over 5 miles. In all of our autonomous flights, no time was spent in manual control.
On board Boreas is a companion computer, the Jetson Orin NX, which is plugged into the flight controller. Also plugged into the Jetson is a Wi-Fi transponder, which is capable of scanning the 2.4 gigahertz frequency for all incoming packets from remote ID transponders. Within these packets from the remote ID contain information regarding the location and velocity of other UASs. Scanning these signals, the Jetson ensures that no vehicle is nearby. If a vehicle comes within 15 feet, the Jetson takes over the autopilot and maneuvers it away from the trajectory of the incoming UAS.
The first one we kind of thought about was a parachute mechanism. It's like the first thing we think about when you want to slow something down that you're dropping. But there was a bunch of problems that came with that. First one was like accuracy. We couldn't really get the payload to fall in a straight line. It would kind of just like go wherever it wanted to, even with like tuning, like cutting a hole in the top of the parachute to channel the air to the center. And then another problem that compounded that was the fact that you have to drop from really high. So we were only dropping from like a 2-story building, and it was drifting maybe 5 feet. So dropping from 150 probably drift like 100 feet or so.
Our original configuration for the ESC setup was to house the ESCs internally inside of Boreas. However, due to space restrictions, we weren't able to make that work. Our second alternative was to try to clip in the ESCs onto the outer edge of Boreas, possibly mounting them on the arms. However, we realized that simply wasn't possible, as the vibrations from the motors would cause the ESCs to shake and risked having the ESCs fall off the drone. So our final alternative was to mount the ESCs onto the side of Boreas in order to ensure that they were securely mounted and they weren't able to fall off.
While designing Boreas and its systems, we took into account potential safety risks and created checklists and safety procedures to follow when flying. In the design of Boreas itself, we implemented lots of redundant systems, including 2 separate power sources for our flight controller, 2 external GPSs, and separate CAN buses for the top and bottom motors, among others. When charging our LiPo batteries, we make sure to have them stored in a protective LiPo bag that is rated for the size of the batteries. When the LiPos are being stored, they are kept in hard-sided ammo cases to minimize the safety risk. During flight tests in autonomous mode, we always have a safety pilot maintaining visual line of sight with Boreas, and in the case that the remote controller loses connection with Boreas, it will return to home and land. Overall, Boreas, its systems, and our operating procedures were designed with safety and redundancy in mind, so they successfully minimize the safety risks as much as possible. During our full mission tests, we practiced setting up and taking down Boreas in a timely manner, and across each of our tests, we averaged 11 minutes and 37 seconds to set up our drone and its ground control station, meaning that we would not go over the provided setup time that we are allowed. While flying the mission, we found that our airdrop system is very reliable, with the payloads dropping within 20 feet of their corresponding ODLC approximately 90% of the time. To be able to complete the entire mission, we decided to implement a battery and payload swap into our mission, with Boreas returning to its starting point after dropping the third payload. This allows us to attempt all payload drops without needing to worry about running out of battery. While performing these pit stops, we took an average of 5 minutes and 12 seconds, meaning that it would not be justified to take a time out to refuel. To complete the mission, we need 3 operators: a safety pilot, a ground control station operator, and a third operator who will be swapping the batteries and payload systems. Overall, the entire mission simulation took an average of 26 minutes and 38 seconds, meaning that we are well within the boundaries of the mission clock. Overall, based on our full mission tests, we would give ourselves a 75% mission score. In conclusion, Boreas and its flight systems have been extensively tested, proving that they are ready to fly the competition mission, and we estimate that our mission score will be approximately 75% of the possible points.